This is section 3.2. In this video, we're going to be talking about mixing problems, a more real-world example of how we can use differential equations. So consider a large tank holding 1,000 liters of pure water. And then picture that there is a brine solution that begins to flow in at a constant rate of 2 liters per minute. If the concentration of salt in the brine entering the tank is 0.3 kilograms per liter, determine when the concentration of the salt in the tank will reach 0.09 kilograms per liter. What I failed to mention is that it is also flowing out of the tank at 2 liters per minute. We're going to let x of t denote the mass of salt in the tank at time t. So the brine enters the tank at 2 liters per minute. This brine has 0.3 kilograms of salt per liter. So immediately let's check our units here. If we take liters per minute and we were to multiply it by kilograms per liter, we would cancel out the liters and be left with kilograms per minute. So multiplying those two values together will give us that the salt is entering the tank at 0.6 kilograms per minute. Now, we can assume that the concentration of salt is uniform throughout the tank. And the reason for that is that the solution is well stirred. When the problem says that, that is to imply that everything is stirred rather uniformly. So, the concentration of salt in any part of the tank is equal to x of t divided by the volume of the fluid in the tank. The rate of flow into the tank equals the rate of flow out. So this is fairly simple. The tank always has 1,000 liters of fluid. What we want is the output rate of salt. This will be measured the same way as the input rate, as kilograms per minute. So we must multiply the 2 liters per minute that the brine or the liquid is flowing out of the tank. And we're going to multiply that by the salt content of the tank. So the concentration of salt in any part of the tank, which is x of t divided by the volume, so divided by 1,000. So we're going to multiply 2 liters per minute by x over 1,000 kilograms per liter. Once again, the liters in the numerator and denominator cancel out, so we do get kilograms per minute. Now, the tank initially contained pure water, so x of 0 is equal to 0. So at first, the fluid flowing in will be much saltier than the fluid flowing out, because the fluid flowing out at the very beginning is going to be almost entirely water until more and more salt comes in and it gets mixed around. So now let's build a differential equation out of this. dx dt is equal to input minus output. So the concentration of salt in the tank is going to be equal to the amount of salt coming in minus the amount of salt going out. So dx dt is equal to the input, which we know is 0.6 kilograms per minute, minus the output, which is 2x over 1,000 kilograms per minute. And we were asked to find out when this is going to equal 0.09, I believe. Scroll back up. Yes, we want to know when x is going to be 0.09 kilograms per liter. So we'll find a common denominator here. We get that dx dt is equal to 600 minus 2x over 1,000. And now this is fairly simple, as by our standards of differential equations, this is separable. So once we simplify it, we are going to get the x's on one side and the t's on one side. And we'll integrate both sides. So we get negative 500 ln of 300 minus x is equal to T plus C. Now, before we go any further, we need to address these absolute values. If it is true that X must be less than 300, then we can drop those absolute values. But if it's possible that X is greater than 300, then we need to keep the absolute values. Let's go up here. Remember, 0.6 minus 2x over 1,000 is our input minus output. So 300 minus x over 500. But we know that there is always going to be more salt coming in than going out. So that means that this number always must be positive, which means that x can be no greater than 300. So because of that, we can turn these absolute value signs into just brackets. Okay, so next we're going to try to figure out what C is equal to. So we are going to enter in our initial value that we knew, which was x of 0 is equal to 0. So we get a value for C. C is equal to negative 500 ln 300. We plug that back in and we get our equation. Now, we want to do as best we can to isolate x here. So we're going to divide both sides by negative 500. Then we're going to, how do we get rid of a ln? We raise both sides as powers of e. So e to the ln just makes those disappear, and we're left with 300 minus x on the left. But we now have e to the power of negative t over 500 plus ln 300 on the right. Well, we can simplify that. E to the power of negative t over 500 plus ln 300 is equal to e to the negative t over 500 times e to the ln 300. When you have e to the ln of anything, it just cancels out. So we get 300 e to the negative t over 500. That's what we have right here. And now we isolate x, because remember, we can drop these absolute values, just act like they're brackets at this point. And we isolate x, we get this 300 times 1 minus e to the negative t over 500. Now, if you'll recall, x over 1,000 is the value that we are actually going to substitute for 0.09. So we can't just substitute x. We're going to substitute x over 1,000 because you need to divide by the volume of the tank. So we divide both sides of the equation by 1,000. And now we can finally plug in 0.09. Okay. Dividing both sides by 3 over 10, we actually end up with 3 over 10 on the left and 1 minus e to the negative t over 500 on the right. Subtract 1 from both sides, divide by a negative. And then how are we going to get this t out of the power of e? Well, we're going to take ln of both sides, because if you have ln of e to the x, that's just equal to x. So if we take ln of both sides, we do get ln of 7 over 10 on the left side, but the right side, we just get to drop that e entirely, and we're left with negative t over 500. So finally, by raising both sides as powers of e, we're left with, oh, sorry, no, we're isolating t here, yeah. So by multiplying both sides by negative 500, we get that t is equal to negative 500 ln 7 over 10. Now, if you want a more real-world solution, that's about 178.34 minutes. After 178.34 minutes, which is what, almost 3 hours, then we will reach 0.09 as our concentration. Okay, assume now that the brine leaves much more quickly. It still enters at 2 liters per minute, but now it leaves at 6 liters per minute. The difference between the rate of flow in and out is now negative 4. So the volume in the tank after t minutes isn't 1,000 liters anymore. It's going down, down, down. So now it's 1,000 minus 4t liters. So the rate that salt leaves the tank is 6 liters per minute times, not x over 1,000 anymore, but x over 1,000 minus 4t. So our new value here is 6x over 1,000 minus 4t kilograms per minute. The problem now becomes input minus output. This is no longer separable. This is actually a linear equation. We have the derivative plus something times the derivative is equal to something else, where these are just functions of t. So we have to get an integrating factor that is e to the power of the integral of whatever is multiplied by x. Now we just stop for a second to actually calculate this integral. We need to let u equal 1,000 minus 4t. So we get that dt, space here for some reason, is equal to negative du over 4. So when we plug that in, we get this negative 6 over 4 that can come out front as a negative 3 over 2 once it's been simplified. But other than that, it's just e to the integral of negative 1 over u, which is negative ln u. We plug in what u is equal to, which is 1,000 minus 4t. So that's where that comes from. And now we're going to use that same law of logarithms that we've been using to take this factor in front of the ln and bring it out as a power. And then e cancels with ln, and we're just left with 1,000 minus 4t raised to the negative 3 over 2. We multiply both sides of the equation by mu. And now the left side, as is always the case, it starts to look a little complicated, but we've done all this for a reason. We know that it is just the derivative of mu times x. So that's how we write it, as the derivative with respect to t of mu times x. The right side of the equation, though, we're going to need to calculate an integral of. So the integral of 1,000 minus 4t raised to the negative 3 over 2. We've already done this substitution. We know that we're just going to end up dividing by that 4. So this 0.6 here becomes negative 0.15. And we get u to the negative 3 over 2. When we integrate u to the negative 3 over 2, we raise this power by 1. So it becomes negative 1/2. And then we divide by 1/2, which is the same as multiplying by 2. So we now have this equation. Isolating x, we get that now x is equal to 6 times 1,000 minus 4t raised to the negative 1/2 minus 3 times this constant c over 20 times 1,000 minus 4t raised to the negative 3 over 2. From here, we plug in our known value that when t is equal to 0, x is equal to 0. So some of these bits will cancel out. And we're left with 0 is equal to 6 times 1,000 to the negative 1/2 minus 3c divided by 20 times 1,000 to the negative 3 over 2. And we're trying to figure out what c is equal to here. So since the whole thing is equal to 0, we can just kind of forget about the denominator. So the numerator is equal to 0. So we get that 3c is equal to 6 times 1,000 to the power of negative 1/2. And that gives us that c is equal to 2 times 1,000 to the power of negative 1/2. So we get this long equation for x in terms of t. But now recall in the previous question, we couldn't just plug in 0.09 for x. We had to plug it in for x over 1,000. Well, in this instance, it's not x over 1,000 anymore that measures concentration. It's x over 1,000 minus 4t. So we need to divide both sides of this equation by 1,000 minus 4t. Now, rather interestingly, if you divide the right side of this equation by 1,000 minus 4t, this negative 3 over 2 in the denominator is going to become negative 1/2. That's just one of the funny things that happens when you start dividing by negative exponents. So now we can perform the substitution. X over 1,000 minus 4t is equal to 0.09. And we simplify the right side of the equation a little bit because we have this common term now. 1,000 minus 4t to the negative 1/2 cancels at least in half of this numerator. And that just becomes 3 over 10. The right side is still a little messy, but we took this 3 times 2 to make 6 and put it over 20 and simplified that as 3 over 10. So we now have a 3 over 10 factor on both of these terms. So we can divide both sides by 3 over 10. And that gives us 3 over 10 on the left. This just becomes 1, and the 3 over 10 just disappeared here. Now the next step is where it's going to start to clean up quite a bit. This 1 will come over to the left side, and then we'll multiply both sides by negative 1 just to make everything positive. So we get 7 over 10 over here, but at this point we're just going to decide these negative 1/2, we're kind of done with those. So if you have a negative exponent, you can just put it, if you have the negative exponent in the numerator, you can just put it in the denominator as a positive exponent. And same with the denominator, you can move it up to the numerator as a positive exponent. So that's what we've done. And instead of writing this as to the negative 1/2 to the negative 1/2, we've just put the roots in. So let's multiply both sides by 10 root 10. That gives us 7 root 10 is equal to the square root of 1,000 minus 4t. We will square both sides of the equation to get 49 times 10 is equal to 1,000 minus 4t. That gives us 490 is equal to 1,000 minus 4t. So 4t is equal to 510. So t is equal to 127.5. So at time 127.5, so just after 2 hours, we will have our 0.09 concentration, which represents, I believe, 9 liters, no, 9, what are we measuring in? All the way back up to the top. 9 kilograms per liter, or 0.09 kilograms per liter.